Hi guys, so welcome to UEXED. You can find us on uexed.com and our batches for, as I pointed out, for net, gate, right, are starting from 1st of May. These are coming in physics category, right? And then of course we are at school. We have separate classes for JEE and NEET physics. You can join us. You can just send us a query and we will reply you back. So that's for the basic information for UEXED. Now let's look at what we are learning. So we are learning statistical mechanics. And in this course, I just pointed out this course is very much designed for UG and PG kind of structure where the basic undergraduate stat mech and postgraduate stat mech we are going to cover. So the exams basically are focused here like JAM and NET, GATE, etc. These sort of examinations and the problem solutions are quite covered here. The theory that we talk about here in the each class is very much kind of will be helpful for your interviews and for your, of course, interest sake. That's the first motto that I would say. And then this would be helpful in all where, everywhere wherever you are, right? So let's look at the first what we have learned. So recap, let me recap a few things for you. So in recap, we have seen that first we introduced to you the second law of thermodynamics, right? So second law of thermodynamics. And in the second law of thermodynamics, we have seen that there's a way to unfold things, right? And for example, if you have a system which is filled with a gas and the system is divided through one box. So if the gas is filled in the system in such a way, there's a pressure gradient establishing in the system. And if you remove this partition, you will see that there's a flow of molecules from this to this, and the molecule is going to fill the entire box, right? So there's a spontaneous flow and spontaneous way of proceeding the event, right? So, and we see that there is a quantity associated with this spontaneous change. So the quantity associated with this spontaneous change is called as entropy. Which we will define with the symbol, let's say S, right? So for entropy, we have seen that we have two equal interpretations. One is Kelvin's and Clausius interpretations, where entropy increases, right? For a spontaneous process that is happening, entropy increases with time, right? And there's a equally Boltzmann approach. Boltzmann definition of entropy was something entropy is connected with counting the states in the system, right? So it is connecting with this basically it's called the way you are going to count the state in your system. So this is basically the Boltzmann definition of entropy, which is associated with the number of microstates in the system. So the idea is to count these microstates in this case. For that, you will need the probability concepts, which we are going to discuss right now. But let's also discuss a few interpretations of entropy. We have seen that the interpretation could be one in kind of like, let's say, order disorder transition. So in the order disorder transition, we see that this basically when you count more states or you have a more accessible state in the system, then of course we consider the system is a more disordered state, right? That's obvious thing. So you can count different states and you can find out what exactly the entropy for that system. The other possible interpretation could be that since due to Boltzmann, which says that basically when we will see the Boltzmann H theorem, so in the H theorem of Boltzmann, we will see that we can define a quantity which is just exactly opposite to the S, and which is just a minus with that. So we will see that that quantity not only always increases, but sometimes it decreases, but with a very less probability, or but however it is, but it's a less improbable event. That's what we call. But it's not always increases as Kelvin's and Cauchy's statement says that it also decreases, right? And because of that, Boltzmann really got a setback in that time, which no one expected. I mean, in a traditional sense, that entropy should have something like that, because no one really much believed the atomic interpretations of the things which we really take today very for granted and things like that. So it was just the Brownian motion and the Einstein interpretations of various things through basically quantum mechanics that led to the more like atomic definitions, more solids, and the latter aspects really, these definitions are really, I mean, powerful and proven to be powerful and have their own interpretations and aspects. But till that time, it was very difficult for people to consider these definitions. There's a other aspects like in term seeing this, we see that for a spontaneous process, there's a quantity which changes naturally, right? And we call this quantity which defines the unfolding of event as probability, right? That's what it is. So, and we see that it always increases. But in the Boltzmann interpretation, we see that these are associated with the number of microstates of the system, and they not only always increases, but there is a time when it also decreases, right? So, but the Boltzmann definition, which is pointed out here in equation 1, is of course applicable with some sort of assumptions. And the number one assumption, like let's say if I say A1, the assumption 1 would be something like that: huge number of particles, and maybe, for example, huger number of microstates. Huge number, right? That's is very essential for this definition to hold true, right? So huge number of microstates is one assumption. Number 2 is something like all these microstates are equally probable. So the probability of occurrence, so that means I would say something like all these microstates are equally probable, right? And number 3 would be, for example, if I talk, we will talk mostly of equilibrium systems, right? So out of equilibrium systems right now, we are not going into detail, but in equilibrium, the number of microstates for a given microstate is almost equal to the total number of possible microstates. That's the assumption, right? So the number of microstates for a given macrostate is almost equal to the total number of possible microstates, right? So and then we see that basically in Boltzmann extraordinary relation, I would say, between entropy and the logarithm of the total number of states did open the door to understand the meaning of entropy. Its interpretation could be associated with the disorder in the system. A large number of states can be conceived as having large number of degrees of disorder. That's one possible interpretation. And this also led to common statement of the second law of thermodynamics. And I would say what the common statement is, that nature proceeds order to disorder. So this is the statement, I would say. I mean, let me build a case philosophically and mathematically. That will be more interesting to look into it, right? So now the question is, having said that, now the question is how these things are happening. We have seen that what the quantity is. We have seen that the quantity is basically entropy. But how these things are happening, that's basically that's very much we are into it right now. So there could be one, if you are the more liking, there's a equal interpretation of entropy on the base of the information theory. And information is a quantity, or rather missing information could be a thing that changes in such a spontaneous process. So I think the other interpretation could comes in terms of information theory, and we will look into it. But before we do that, let's talk about the few concepts of the probability. Because why? Because we have seen that in the Boltzmann interpretation of entropy, it's basically the counting of the states. I mean, you need the logarithmic of the states. That's what you need, right? So basically, all what you are going to do is basically you are going to count the total number of states for the system that could have for a given energy or number of particles or volume, right? That's what we need. For a given specified condition, we need to count the number of states for the system to have. And once we do that, we can write down the entropy of the system, right? But before even we do that, we need some definitions of probability, because it's very essential, right? Because otherwise, how you are going to count the states, right? So what probability is and things like that. So let's look the Kolmogorov's axiomatic approach basically. So it's basically formulated in 1930. So first of all, you need to define a sample space. So what the sample space is? Sample is a set of all possible outcomes of a given defined experiment. So it could be for example, if I throw a dice, right? So what could be the space, or what I say technically sample space? The sample space would be the set of all possible outcomes, like for example, 1, 2, 3, 4, 5, 6. Okay, so this will be the sample space for a dice. For example, now if I look at the second example, I say for a coin, what will be the sample space? The sample space for a coin would consist of head and tail, right? That's all, two things. So, and then basically the second thing is to define for you is the collection of events, right? Collection of events. So collection, an elementary event or a collection of event could be anything. For example, I can say that when I throw the dice, I could constrain myself to such that the throwing will result to an outcome of even number. So in that case, the event will be denoted by something 2, 4, 6. Right? This will be my possible set of events, right? Collection of events. So that's all. So I need the collection of events. I need to define my set, and the third thing, I need to define my probability. So to each event, what I just previously mentioned with the symbol E. So with each event, I can associate, or I can refer the probability of that particular event, right? But such that the probability will be such that it will be lie between 0 to 1. For example, if I say P is the probability of my event, it will be lying something between 0 to 1. And then for a certain event, if I say event is certain, for example, Q is going to for a certain event, you will see that it will associate, or I would say something like that. For an impossible event, probability will be 0. And for two disjoint event or mutually exclusive, or I say disjoint, let's say. For two disjoint events, the probability of occurring of both events will be the sum of indivisible ones, right? So these are the few set of rules that we are going to follow for probability. So for today's lecture, we are going to wind up it here. For more lectures, join our classes, which are going on regularly. Thank you for joining today's class. Thank you.